Okay, let's jump right into this explainer. This is part 3 of our Zero to Hero VDA 50/50 series, and today we're enthusiastically decoding the entire journey of a transport order from creation all the way to completion. We're looking at the complete life cycle of a mission, literally from the exact millisecond it's created by the master control system right up to its successful physical completion by the robot out there on the warehouse floor. Getting this right is absolutely crucial. Think about a busy facility where the master control is orchestrating hundreds of robots all at once. If this life cycle breaks down, you don't just get a delayed package. No way. You get physical warehouse collisions, stalled operations, and an absolute logistical nightmare. So understanding this flow is definitely your key to mastering automated fleet management.
We have a fantastic roadmap lined up today. We'll be hitting 5 key areas. 1. Mapping the transport order. 2. The base and the horizon. 3. The order acceptance procedure. 4. Tracking vehicle state progression. And finally, number 5, extending and completing orders.
So, the VDA 50/50 state machine actually operates across 5 core, uncompromising phases. We start with ingestion, move right into validation, step into active progress, require a base extension to keep moving, and finally, we hit completion. Breaking this lifecycle down into these strict phases is exactly how the standard prevents multi-vendor chaos. By strictly defining the roles of engagement here, a robot from brand A and a totally different robot from brand B both know exactly when an order transitions from being a mere suggestion into an active, concrete command. There's zero room for interpretation, which keeps the entire warehouse running in perfect synchronization. Let's walk through how this actually plays out in practice.
Starting with Section 1, Mapping the Transport Order, the Blueprint of a Mission.
Whenever the central brain wants a robot to move, it mathematically links physical destinations together using a JSON order schema. Under the VDA 50/50 standard, a transport path is essentially a topological graph made of alternating nodes and edges. Think of nodes as your 2D coordinates on the floor, and the edges as the logical paths that connect them. To make this totally foolproof, the standard enforces a really strict sequenceId rule. Nodes are always assigned even numbers, and edges are always odd. Imagine the warehouse floor for a second, right? Node 0 might be the charging dock where the robot wakes up. Edge 1 is the physical aisleway it travels down. And Node 2 is the pickup rack at the end of that aisle. By mathematically forcing nodes to be even and edges to be odd, starting from 0, the robot parses a JSON sequence like 0, 1, 2, and instantly understands the continuous, unbroken chain of its route. It knows exactly how everything connects without having to do any guesswork whatsoever.
Moving on to Section 2, the base and the horizon, or in other words, permission to move.
Once that route is mapped out, the robot needs to know what it is actually permitted to drive right now. In the JSON payload, this is controlled by a simple Boolean called released. If released is true, it's the base. The base is cleared for immediate execution, and it absolutely cannot be modified once sent. But if released is false, it's the horizon. That's a planned future route that the master control can still alter. Think of it kind of like a GPS versus a traffic manager. Your GPS knows the final destination all the way across town, right? That's your horizon. But the traffic manager only gives you the green light for the next 2 blocks. That's your base. This distinction is absolutely critical in a dynamic warehouse. Say a human-driven forklift suddenly blocks an aisle up ahead. By keeping the horizon unreleased, the master control retains the ultimate power to seamlessly rewrite the robot's future path before it gets stuck in that traffic jam, all without having to cancel the active base operation the robot is currently executing.
Which brings us to Section 3, the order acceptance procedure, also known as the strict bouncer. Before a robot moves a single inch, it scrutinizes the incoming data payload during the order acceptance procedure. It genuinely acts like a strict bouncer at a club, rigorously checking 3 main things. First, it validates the JSON structure itself. Second, it checks its own hardware capabilities against its internal vehicle fact sheet. And third, it verifies the order identifiers. If any of these fail, the consequences are severe. If a robot gets a malformed JSON, it throws a validation error to prevent a full network crash. Even more critically, if the payload asks the robot to lift a pallet higher than its physical limits actually allow, it completely rejects the task with an order error. These strict checks are there to protect the physical hardware from catastrophic, dangerous errors on the floor, while also shielding the software network from collapsing under bad data.
Now, how does it keep track of the missions themselves? That's where the orderId and orderUpdateId come in. The vehicle uses these 2 specific identifiers to seamlessly handle network drops, ignoring duplicate messages, and only ever accepting valid updates. You know industrial Wi-Fi can be notoriously spotty? right? Imagine a scenario where the network stutters and the master control panics, spamming the exact same command message 3 times in a row. Well, the robot just calmly looks at the orderUpdateId. If it receives an order it is already executing, the duplicate is safely filtered out as background noise. If the orderUpdateId is lower than its currently active ID, it throws an error. The system relies entirely on this counter to guarantee that the robot only accepts true, forward-progressing updates to its mission.
Let's step into Section 4, Tracking Vehicle State Progression, the live broadcast.
With the order accepted, the robot begins its physical journey. But it has to constantly broadcast its live progress back to the master control via the state schema. Instead of just pinging raw GPS coordinates over and over, the vehicle maintains 2 specific arrays in its state payload: nodeStates and edgeStates. As the robot physically completes a segment, say it finishes driving down an aisle, it literally deletes that edge from the edgeStates array in its local buffer. The fleet manager gets to watch these arrays shrink in real time. This brilliantly illustrates how the central control knows exactly what is left on the active base path, without ever having to guess based on elapsed timers or imprecise coordinate tracking.
Now, of course, robots don't just drive, they actually interact with their environment. For physical tasks, the vehicle reports its action states, stepping through a standardized progression matrix: waiting, initializing, running, and then either finished or failed. And here's a really cool addition. Version 3.0 of the standard introduced a retriable state for failed attempts. Let's say a robot is trying to use a barcode scanner, but there's a little dust on the label. Before version 3.0, a failed scan might trigger a fatal halt, requiring a human operator to physically walk all the way out to the floor and reset the machine. Now, the system can flag that action as retriable, automatically attempting a second pass based on a direct trigger event. It literally saves an immense amount of operational downtime.
The execution flow of these action states is tightly regulated by a parameter called the blocking type, which dictates exactly how an action interacts with the vehicle's movement. A none-blocking type means the robot can do things like flash its lights or sound its horn in parallel while driving. But let's walk through a more complex narrative. Imagine a robot approaching a critical drop-off point. It might use a soft block to keep driving right up to the exact target node, but once it gets there, it uses a hard block to force the vehicle to halt completely, ensuring it is entirely stationary and safe before deploying its heavy steel forks. Version 3.0 also added a single block, which allows driving to continue but prevents any other single blocking actions from triggering at the exact same time. It's an incredibly precise way to choreograph complex mechanical capabilities.
So what happens when the robot runs out of release track? If it only has base permission for 2 blocks, won't it just hit the brakes and come to a dead stop at the end of block 2?
Well, let's answer that in Section 5, Extending and Completing Orders, Passing the Baton.
To maintain a smooth, continuous flow of movement, the standard actually relies on a specific handshake to extend the robot's permission to drive. Picture a robot moving at top speed down an aisle. As it nears a pre-configured decision point towards the end of its base, it doesn't slow down at all. Instead, it triggers a flag setting new base request to true. In mere milliseconds, the master control responds. It increments the orderUpdateId and instantly flips those unreleased horizon edges into a new actionable base. By dynamically passing the baton like this, the planned horizons are converted into active commands on the fly. This prevents massive mechanical wear and tear on the motors that would otherwise be caused by constantly stopping, requesting permission, and then starting up all over again.
Eventually, the task comes to an end. But when is the robot actually free for its next job? A vehicle is only truly idle if its nodeStates array is completely empty. Otherwise, it is executing, even if it's physically paused. This is a crucial, non-negotiable rule to prevent the absolute disaster of double booking. Imagine a robot is waiting at a station for a conveyor belt to load a pallet onto it. It is physically parked and standing totally still. If the master control assumed it was idle and sent a brand new mission right then, the robot might just drive away without its cargo. Because that conveyor belt node is still sitting in its array, its state remains executing. Master control knows to strictly keep its hands off until that array is totally clear. It's the ultimate failsafe.
I hope this explainer empowered you with a clear understanding of the VDA 5050 order lifecycle. By mastering how nodes, edges, bases, and horizons all work together, you've completed the foundational zero-to-hero knowledge of how these automated machines actually think and move. But here's something to think about. As mobile robots transition from strict line following to free open navigation, how will standards like VDA 5050 evolve to balance localized autonomous decision-making with central fleet safety?
With version 3.0 already bringing in path sharing and dynamic zones for freely navigating robots, this standard is evolving rapidly. Thank you so much for joining me to decode this standard, and I'll catch you in the next explainer.